Recall, when we first started talking about systems of differential equations, we wrote each independent variable in its own differential equation. Our example y prime equal to 5, negative 2, negative 1, 5 times y that we just studied could have also been written component-wise as x prime equals 5x minus 2y and y prime equals negative x plus 4y. It was only once we started learning about matrices did we change from the second form here into our matrix representation of this linear system of differential equations. And once we wrote this system of differential equations in its matrix representation, we were able to find the general solution y of t equals c1 e to the 3t times 1, 1 plus c2 times e to the 6t times negative 2, 1, where 3 and 6 were the eigenvalues of A, and 1, 1 and negative 2, 1 were the associated eigenvectors. But what about the scalar functions x of t and y of t? Have we found those? To find each of these components of our vector function y, we want to write y, which is xy, as one single vector. To do this, let's first observe that we can multiply each vector 1, 1 and negative 2, 1 by their scalar multiples. That is, we can do c1 e to the 3t times the vector 1, 1 and c2 times e to the 6t times the vector negative 2, 1. This will give us that y of t equals c1 e to the 3t, c1 e to the 3t, plus negative 2c2 e to the 6t, c2 e to the 6t. And now we can add these vectors component-wise to get that y of t is c1 e to the 3t minus 2c2 e to the 6t and c1 e to the 3t plus c2 e to the 6t. But on the other hand, y of t is the vector function xy. So by writing y as one vector, we get the solutions x and y as the components of y. X equals c1 e to the 3t minus 2c2 e to the 6t, and y equals c1 e to the 3t plus c2 e to the 6t. There may be cases where we want to leave our solution as a vector function or look at each component one at a time. So it's good to be able to go back and forth between these two representations of our solutions.